Let's talk about the ideal gas law. So generally speaking, all the gases that we see in this class are going to be treated as an ideal gas. So remember, we introduced solids, liquids, and gases, and we talked about some of the differences between them. So an ideal gas is one that is operating far away from its critical pressure and temperature. At ambient conditions, near room temperature and sea level, things like air, oxygen, nitrogen, carbon dioxide, etc., can safely be assumed to be ideal gases. There are substances that do not behave as ideal gases, and those are denoted as non-ideal gases, but we're not going to deal with them extensively in this class. I just want you to be aware that they exist, and they apply to substances that are gases but are operating near their critical temperature and pressure. Okay? But on to the ideal gas law. The ideal gas law is governed by this equation that you see on your screen. Okay, so pressure P is equal to the multiplication of the density times the gas specific constant times the temperature in absolute units. I'm sure you've seen the ideal gas law before, probably in chemistry, I'm guessing, but you probably saw it in slightly different form. So in other words, you probably saw it like this. So pressure times volume is equal to the number of moles times the universal gas constant multiplied by temperature. So PIV-NERT is the way that most people learn it. This equation is identical to the one that you see here, but this is the form that's just more convenient for fluid mechanic applications, so we work with it in those units. Okay, the universal gas constant, hopefully you remember, is the same for all ideal gases. It's something like 8.31 something something in the SI unit system. So that is the universal gas constant. And the difference between this gas-specific one here and the universal gas constant here is just the following. So the gas-specific gas constant is the universal gas constant divided by the molar mass. Okay, I forget how your textbook differentiates molar mass from regular mass, but I'm just going to put a hat on top of it. So, and I'll also write a note here, molar mass. Okay, we all remember what this is, right? You can get the molar mass of atoms from the periodic chart based on its numbers. So the molar mass of helium would be 2, for example. Oxygen is, oxygen is actually a molecule, O2. So the molar mass of oxygen would be 2 times 16, because oxygen is 16 on the periodic chart, or 32. Okay, so anyway, hopefully we all have the idea on that. All right, temperature, just a reminder, has to be in absolute units. So if you see something like degrees C or degrees Fahrenheit, you need to switch that over to Rankine or Kelvin before you use it in this law. Also, make sure that the units match left and right hand side. Okay, so units must match. Okay, of particular importance, the units of R are usually what dictate the units of pressure, so just keep an eye out for that. Okay. Another property that you often see in fluid mechanics is something called the specific weight. And that usually has a symbol of capital gamma, and that's just defined as the density times the gravitational constant. Okay, we know that that is 9.81 in the SI unit system and 32.2 feet per second squared in the traditional system. Okay, so hopefully this answers your questions on the ideal gas law.